So our goal here is going to be to talk about rings, define what a ring is, give lots of examples of rings, and also talk about the various different types of rings we'll encounter and properties that they might have. So we'll start with binary operations. So let A be any set. A binary operation on A is just any function from A cross A to itself. And the key idea here is we want to take two elements of A, so we want to take a pair of elements of A and combine them and create a new element. We'll refer to this element as A dot B. So the common notation for dot of A comma B will just be A dot B. So let's look at a few examples. So the first example, a very natural operation we've been studying, is addition. And addition is an operation from Z cross Z to Z. And what does this operation do? It takes a pair of elements and it gives back their sum. So for example, we can write plus of 3 comma 5 is 8. And of course, normal people don't write functions this way. Normally, we just write 3 plus 5 is equal to 8. Right? But this is an example of a binary operation. Another example, something maybe a little bit more complicated, let's consider M2 of R. So this is going to be the set of all 2 by 2 matrices with real entries. Okay, and operation that we know is matrix multiplication. So for example, matrix multiplication from M2 of R cross M2 of R to M2 of R, this is a binary operation. So I can say take a matrix A, take a matrix B, and give back their product A dot B. So for example, I can let A be the matrix 1, 2, 3, 4, B be the matrix 1, 1, 1, 1, and A dot B is of course their product, which we would write as 1, 2, 3, 4 times 1, 1, 1, 1. And what would this give me back? This would give me the matrix 3, 3, 7, 7. Okay, so these are two examples of binary operations. We can of course define all sorts of binary operations. We can define, for example, I'll call this operation star from Z cross Z to Z. And the way I'll define this operation is I'll say it takes a pair A comma B and it gives back A squared plus B squared minus 1. So for example, the star of 3 comma 5, this is going to be 3 squared plus 5 squared minus 1, which is going to be 33. All right, so in this case, we would just say 3 star 5 is equal to 33. So anything we can write down, any kind of function from Z cross Z to Z is going to be a binary operation on Z. When we study rings, when we study groups in this course, the thing that we're going to be really focused on is operations which are kind of natural or satisfy certain properties. So we'll see that the star operation is not going to be an operation that we find too useful. Okay, so we can finally define one of our main objects of study. So we're going to start with a non-empty set R, and we'll assume that the set has two binary operations defined on it. So there's an operation of addition, which we'll call plus, and an operation of multiplication, which we'll call times. We'll write it with a dot. And a set with these two operations is going to be called a ring if it satisfies the following properties. Now, these properties are going to look quite natural because we've already seen that the integers satisfy these properties and the integers mod n satisfy these properties. So we already have two examples of rings, but let's recall some of the properties that we saw in the last video. So the first property is that if A and B are elements of my ring, then A plus B also has to be an element of my ring. And this is called closure under addition. This just holds from the fact that we have a binary operation. We'll see that this becomes important when we talk about subrings, though. Okay, so we have that it's closed under addition. If I add two elements of R, I create a new element of R. We have that the addition is associative, so that A plus B plus C is the same as A plus B plus C. We have that addition is commutative. A plus B is always equal to B plus A. We have the existence of what is called an additive identity. So there's something that plays the role of 0. So we're going to call this 0 sub R. And this is an element such that when I add any A to it, I get A back. So A plus 0R is always equal to A. So this acts like the number 0 did in the integers. Finally, if A is any element of R, then there is a b in R such that a plus b is equal to 0R. So these, what we'll call b the additive inverse of a. We'll show that it's unique in the next video. But this is just saying that if I have an element of my ring, there's always something I can add to it that gives me back 0. Okay, so these are the properties we'll assume that addition satisfies, right? So our addition operation satisfies these properties. Notice we haven't mentioned multiplication yet, and we'll do that now. So what properties should multiplication satisfy? Well, we should have closure. If I take any two elements of my ring and I take their product, I multiply them together, I should get an element of my ring back. So if a and b are in R, then so is a times b. We'll also assume that the operation of multiplication is associative, so that a times bc is the same as ab times c. Okay, so these are the assumptions we're going to make on multiplication. Those are the only assumptions we're going to make. And the question now is, well, what do these two operations have to do with one another? It seems like we have two separate structures going on. We have some rules that addition satisfies, some rules that multiplication satisfies, but we don't have any way of those operations interacting. So what am I going to do? I'm going to introduce what's called the distributive law. So a times b plus c is equal to a times b plus a times c, and a plus b times c is just a times c plus b times c. So this gives us a way of having addition and multiplication interact, and now we can study rings, because until we introduce these distributive laws, we basically just have a set with two operations, and those two operations have nothing to do with one another. These distributive laws that we've introduced allow these two operations to interact. Okay, so this will be our definition of a ring. Okay, so as we've seen, a ring is something that satisfies the rules 1 through 8 that we just listed. Now, there are other properties, well, there are other kinds of rings that we'll encounter, and I kind of want to talk about these for the time being. So the first will be what's called a ring with identity. So a ring with identity is a ring, so it satisfies the rules 1 through 8 that we just listed, but now we're going to assume that there's a special element 1 sub r in my ring, such that a times 1 sub r is always equal to a, and 1 sub r times a is always equal to a, and this is true for all a and r. Okay, so this is something that behaves like the number 1. So depending on what source you use, depending on what book you read, certain books will assume that all rings have identity, so they'll call a ring what we're calling a ring with identity, and certain books will assume rings don't have identity by default. So for our purposes, for our future videos, we're going to assume that a ring does not necessarily have a multiplicative identity, and ones that do, we'll call them a ring with identity. Okay, so this is the first type of ring. Another property we might have is the commutative property. What if multiplication is commutative, right? We call this a commutative ring. So a commutative ring is one in which a times b is equal to b times a for all a and b in R. Okay, so this is what we'll call a commutative ring. Okay, so we're finally ready to discuss some examples of rings. And the first examples I'll draw your attention to are the integers, the rationals, the reals, the complex numbers, and z mod n with their usual operations of addition and multiplication. So these satisfy the rules on our list, and moreover, the multiplication is commutative, so they're commutative rings, and they all have an element which is a multiplicative identity. So in the case of z, q, r, and c, this is the number 1, and in case of z mod n, it's the equivalence class of 1. Right, so we have a multiplicative identity. Okay, so these are examples of rings. These are very common examples, but let's look at some more interesting examples. So the first example we'll look at is the set of even integers. So why is this a ring? Well, let's check that it satisfies our axioms 1 through 8. First, let's check closure under addition. And all this property is saying is that if I take two even integers and I add them, then their sum is also even. So if I combine two evens, I should also get an even back. Okay, so we'll let a and b be even. Well, what does it mean for them to be even? By definition of our set, it means that a can be written as 2 times n, b can be written as 2 times m, for some m and n and z. Okay, well, let's add these together and see what happens. If I look at a plus b, that's just 2n plus 2m, and I factor out a 2, and this is 2 times n plus m. So I have 2 times an integer, and so I'm granted entry into the set E. This is going to be an element of the set E. Okay, so that's closure under addition. Again, all it's saying is that the sum of two even numbers is even. Associativity of addition and commutativity of addition, they hold in Z, so therefore they must hold for the evens, right? The evens are just a subset of Z, so these two properties get inherited from Z. We also know that 0 is in my set E, since 0 can be written as 2 times 0. So we have a 0 element. We have an additive identity. We know that if A is even, then, well, we could write A is equal to 2n for some integer n, which means that negative A is 2 times negative n, and that's also even. And moreover, A plus negative A is equal to 0. Okay, so we have the existence of additive inverses inside of E. Okay, let's check multiplication now. Well, we have that E is closed under multiplication. If I take two even numbers and I multiply them, I get an even number. So let's try this. If A is 2n and B is 2m, then their product is 2n times 2m, which I can just write as 2 times 2mn. So I have 2 times an integer, so this is an element of E. So I have closure under multiplication. And I also have associativity of multiplication, the distributive laws, and commutativity of multiplication. Why? Well, they hold for all integers, so in particular they have to hold for the even integers. So I have these satisfied. And finally, I might ask, well, what about the multiplicative identity? Well, I'll notice that 1 is not an element of E, so E does not have a multiplicative identity. So we would call E a commutative ring. Finally, we might ask the question, well, what about the odd integers? Do those form a ring? Well, this one actually has a very easy answer that we can write down. Well, the thing we might notice is that it's not closed under addition. So for example, if I were to take two odd integers, 3 and 5, these are odd, we know that 3 plus 5, this is 8, this is not an element of O, right? 8 is an even integer, so we see that O is not closed under addition, so this is an example of something that is not a ring. Okay, so this is not a ring. Another important example of a ring will be the ring of 2 by 2 matrices over the reals, or for that matter, the ring of n by n matrices over the reals. The same properties will hold. So we'll define matrix addition in the following way. So this is the usual matrix addition, and we'll define matrix multiplication in the usual way. So this is for 2 by 2 matrices, and we'll see what properties hold here. Okay, so the first property we need to check is closure under addition. Well, by definition, if I add two matrices with real entries, I'm just summing their entries, so the sum of real numbers is always real. Right, so these entries always end up being real numbers. So I have closure under addition. This is pretty straightforward. Many of the other axioms are quite tedious to check, so we'll check that addition is associative, and I'll leave several of the others as exercises because they're just quite tedious. We'll just use properties of the real numbers to do it. Okay, so let's check associativity of addition. So I'll let A, B, and C be the following matrices, and I'll start with A plus B plus C. Okay, so let's write this out. So I'll write A out, and B plus C, I'll add them together. So if I add the matrices B plus C, I get the following matrix. Okay, so this is A, this is B plus C. Okay, let's combine these. So this is, what am I doing? I am adding A2 plus A3 first, and then adding A1 to that. I'm adding B2 and B3 first, and then adding B1 to that. Okay, so when I do that, I have an expression that looks like the following. I have A1 plus A2 plus A3. I have B1 plus B2 plus B3. Okay, well, what do I know? These are real numbers, and I know that the real numbers are associative, so I can move these parentheses. So in each one of these entries, I'm going to move the parentheses. I'm going to use the fact that the real numbers are associative to move these parentheses. So now this entry is the same as this entry is the same as this entry, so on and so forth. And once I've used associativity of the reals, I'm now going to pull this apart. So now I'm going to say, okay, well, this can be written as the matrix with entries A1 plus A2, B1 plus B2, C1 plus C2, and D1 plus D2, plus the matrix with entries A3, B3, C3, D3. All right, so if I were to combine these again, I would do A1 plus A2 first, and then add A3 to that, and that's exactly what this expression is. Okay, so I've pulled them apart, and what do I notice right away? I notice that this is just A plus B plus C. Another thing I'll note here is that properties 3, 6, 7, and 8 are all very similar, and they're similarly tedious. So 3, if you recall, is that addition is commutative. 6 is that we're closed under multiplication, so that just follows from definition. 7 is that multiplication is associative, and 8 is the distributive laws. So the proofs are similar. We basically combine everything, use some properties of the real numbers, and then pull everything apart, and I'll leave those as exercises. Okay, well, what about some of the other axioms? Well, we know that there's a zero element, there's a zero matrix, which is just the entry 0, 0, 0, 0. So I know that A plus 0 is always equal to A for any matrix A. So this is the zero matrix. I also know that if A is a 2 by 2 matrix, so A is A, B, C, D, and B is the matrix negative A, negative B, negative C, negative D, then A plus B is equal to 0. And moreover, if A is A, B, C, D, these are all real entries, then B is negative A, negative B, negative C, negative D. These are all real entries, and their sum is equal to 0. So we have that axiom 5 holds. Okay, so we have a ring at this point, right? We've checked all our axioms. What else is left to check? Well, we can ask, does this ring have an identity element? Well, the answer is yeah. I have this identity matrix. So this identity matrix satisfies the property that A times I is always equal to A, and I times A is always equal to A. So this is a ring with identity. We can ask, is this ring commutative? So I can take A to be, let's check. We'll produce a counterexample to show that this ring is not commutative. A is 1, 2, 3, 4. B is, let's say, 1, 1, 1, 1. If I do A times B, right, so this is 1, 2, 3, 4 times 1, 1, 1, 1, I'll get, as a result, 3, 3, 7, 7. If I do B times A, well, let's see what I get. I get 1, 1, 1, 1 times 1, 2, 3, 4. And if I use my definition of matrix multiplication, I'll see that I get 4, 6, 4, 6. Right? So it's clear that A times B and B times A are not the same. So this ring is not commutative, but it has identity. So we'll say that M2 of R is a ring with identity. So this is a ring with identity. Okay. So we have a ring with identity. One comment that I'll make is that the real numbers here can be replaced with any commutative ring. So the entries don't specifically need to come from the reals. They can come from any commutative ring. So we'll be studying matrices with entries in, say, Z mod 6, or matrices with entries in Q, or matrices with entries in Z, right? So any commutative ring can be put in place, and M2 of that ring will still be a ring with identity. So to kind of clarify this a little bit, if R is any commutative ring, then we can similarly show that M2 of R is also a ring. If R is a commutative ring with identity, so in addition to being commutative, if R is a commutative ring with identity, we can show that M2 of R is also a ring with identity. Okay, so we'll be studying examples like this. So let's consider another example of a ring. So I'm going to consider the set capital F to be the set of all functions from the reals to the reals. We can define addition and multiplication on the set, so we'll just define F plus G to be defined by pointwise addition, and F times G to be defined by pointwise multiplication. And one thing we can show if we go through our axioms is that this is a ring, and moreover, this is actually a commutative ring with identity. So the identity function is actually the function, I'll call it 1 of x. It's just defined to be 1, right? The real number of 1. What's the additive identity? The additive identity 0 of x is just equal to 0, right? So this is another example of a ring. Okay, and here's kind of a rather strange example of a ring. So ring structures need not come from natural objects. So what I've done here is I've defined a set A, B, C, D, right? Those are the 4 elements of my set, and I've defined some kind of addition and some kind of multiplication via tables, right? So this is saying, for example, that B plus C is equal to D, right? And similarly, C plus B is equal to D. Okay, so we'll take a few things for granted. We can check certain things manually, so checking associativity of addition, checking associativity of multiplication, and checking the distributive laws. These are super tedious, and if you want to check them case by case by case by case, feel free to do that. Okay, so we'll take those for granted. We'll say that those have been checked. We can check some of the other axioms. We can ask ourselves, is addition commutative? Well, let's take a look. We have that a plus a is a. Great. A plus b, that's b. B plus a, that's b. Great. A plus c, that's c. C plus a, that's c. A plus d is d. And d plus a is d. Right? So we can check that, you know, we can go through case by case and check, is addition commutative? We can do, for example, b plus a is equal to b, and a plus b is equal to b. B plus c is equal to d, and c plus b is equal to d. We can check b plus d is equal to c, and we can check d plus b is equal to c, right? So we can go through one by one and check addition is indeed commutative, right? And this is super tedious to do, but we can do it. Okay, what about the existence of our zero element? Well, we can ask ourselves, is there an element in the set that when I add it to any other element, I get the same element back? So what do I mean by this? Well, let's look at a. If I take a plus a, I get a back. If I take a plus b, I get b back. If I take a plus c, I get c back. If I take a plus d, I get d back, right? So what I notice is that my zero element in this ring is actually a. If I add a to anything, I get that anything back. If I do a plus b, I get b back. If I do a plus c, I get c back. Okay, so the zero element is a. What about additive inverses? Is there a way to return to our zero element? Is there a way to return to a? Well, let's think about it. I know that if I take a and I add a, I get a. Or if I do a plus a, I get a. What about b? What can I add to b to give me my zero element? So if I look at b and I look at b plus b, I get my zero element back. So b plus b is equal to my zero element. What about c? Well, if I look at c plus c, I get back to my zero element. So c plus c is equal to my zero element. And similarly, if I look at d, I get that d plus d is equal to my zero element. So I have additive inverses. Okay. What else do I have? What else do I not have? If I look at the multiplication table, I'll see that there's no element that behaves like 1. So we won't have a multiplicative identity. I can ask, is this commutative? Well, let's take a look. So there's no 1 sub r. There's no element that when I multiply it on the left and on the right against something, that I get that something back each and every time. And we can check that manually. We just have to go through case by case by case and check that none of them are a viable candidate. Okay, so like for example, I see that a times c is equal to a, but that c times a is equal to a. So I might say, okay, maybe c is my candidate because I see that c times a is a and a times c is a. Well, let's take c times some other element. If I do c times d, I get c back. But if I do d times c, I get d back. So c is not my 1 because d times c gave me back d, but c times d didn't give me back d, it gave me back c, right? If c is my candidate for my 1, I should have that c times d is equal to d, but I'm getting c back over here. So I see that that doesn't work. But it also leads me to discover that I don't have commutativity. For example, I might notice that c times d is equal to c, but that d times c is equal to d, right? So this is also not commutative. So this is just a ring. It's not commutative. It has no identity. Okay, so this is kind of a weird example. Okay, so now we'll talk about special kinds of elements in rings that we'll encounter. And the first kind of element we'll discuss is what's called a zero divisor. So we've already encountered this in earlier videos, but what is a zero divisor? So a zero divisor is a non-zero element of my ring, so we'll call it A, such that I can multiply it by some other non-zero element, either on the left or on the right, and produce 0. So it's an element that's non-zero that can be multiplied by something else that's non-zero to give me back 0. So this is called a zero divisor. So we've already seen examples. So our first example is, let's consider the ring Z mod 6. And the thing that I might notice is that 2 times 3 is equal to 6, which is 0 in Z mod 6, but 2 is not equal to 0, and 3 is not equal to 0. So we would call 2 and 3 are zero divisors. These are examples of zero divisors. So 2 is a zero divisor and 3 is a zero divisor. 4 will also be a zero divisor because 4 times 3 is equal to 0 in Z mod 6. So this is an example of a zero divisor. What other examples are there? Well, what if I let my ring be the set of 2 by 2 matrices, let's say over the reals? I can consider the matrix A to be 0, 1, 0, 0, and the matrix B to be 0, 2, 0, 0. One thing I'll notice right away is that A times B, this is 0, 1, 0, 0 times 0, 2, 0, 0. This is 0, 0, 0, 0. And so we see that A and B are both zero divisors. They're two non-zero objects that I can multiply and get my additive identity. So we'll say that A and B are zero divisors. And one thing we'll notice that in general, if A and B are not invertible and non-zero, then rather if A is not invertible and non-zero, then A will be a zero divisor. So in general, if we have this matrix A, which is A, B, C, D, and AD minus BC is equal to 0, then I can do ABCD times D minus B minus CA. And what is this going to give me? Well, if I do the product, I'll get AD minus BC as this entry, minus AB plus AB as this entry. I'll get CD minus CD as this entry, and I'll get minus BC plus AD as this entry, and I'll see that this is just 0, 0, 0, 0. So in general, any non-zero matrix which isn't invertible is a zero divisor. So these are quite common in rings. Okay, so we actually have a special name for certain kinds of rings that don't have zero divisors. So if R is a commutative ring and it has identity and it doesn't have any zero divisors, then we call R an integral domain. So there's some nice examples of integral domains. So Z is an integral domain, Q is an integral domain, R is an integral domain, C is an integral domain, and also Z mod P, where P is prime. These are integral domains. Right, one of the properties that we proved about Z mod P in an earlier video was that Z mod P had no zero divisors. We showed that P being prime is equivalent to B times C being 0, implying that B is 0 or C is 0 in Z mod P. So we showed that Z mod P had no zero divisors. What's an example of something that's not an integral domain? Well, Z mod 12 is not an integral domain. And why is that the case? Well, 3 times 4 is equal to 0, but 3 does not equal to 0, and 4 does not equal to 0. Right? And in general, Z mod n, when n is composite, is not an integral domain. So Z mod n for n composite is not an integral domain. And the key thing to notice is that we're considering commutative rings with identity here when we're defining integral domains. Okay, so this is the first kind of ring we're going to encounter and talk quite a bit about. Okay, so another type of element that we'll encounter is what's called a unit. And units live specifically in rings with identity. So we'll require that our ring has a multiplicative identity. And what is a unit? A unit is basically an element of the ring called A, which is invertible under multiplication. So I can multiply A by some other element of my ring and produce 1. So we'll call that other element U, and we'll say A times U is 1, and U times A is equal to 1. So this is an example of a unit. So let's look at some examples of some units. So in Z mod 6, 5 is a unit. Why is 5 a unit? Well, since 5 times 5 is equal to 1. All right, 5 is its own multiplicative inverse. We can also say in Z mod 6, 2 is not a unit. Why is 2 not a unit? Well, I can go through and check that 2 can't be multiplied by anything to give me 1. Right? I might notice that 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3, well, that's 6, so that's 0. 2 times 4 is 8, so that's 2. And 2 times 5 is 10, so that's 4. All right, so there's nothing I can multiply 2 by in order to give me back 1. Okay, so I'll see that 2 is not a unit in Z mod 6, 5 is a unit in Z mod 6. What are some other examples? Well, consider the ring of 2 by 2 matrices over the reals, M2 of R. I'm going to say let A be the matrix A, B, C, D in R with AD minus BC not equal to 0. So we'll assume that the matrix is invertible. I can define the matrix B, or let's define the matrix U, let's call it U, is 1 over AD minus BC times D minus B minus C A. And one thing I can note is that what I've just defined is the inverse of A, and we have that A times U is the identity, and U times A is the identity. All right, so A is a unit. So what we've managed to show is that if A is a 2 by 2 matrix, it's either 0, a unit, or a 0 divisor. Okay, so that's kind of interesting. Okay, so these are 2 examples of units that pop up in rings. What about some easier rings? Well, let's look at the ring Z, the ring of integers. The units here, the only elements I can multiply, the only integers I can multiply by another integer to produce 1 are 1 and negative 1. So those are the only units. If I look at an integer like 2, I can't multiply 2 by another integer to produce 1. So 2 would not be a unit inside of Z. Okay, so the only units inside of Z are 1 and negative 1. What about the rational numbers? So R is equal to Q. Well, let's take a look at this. If A is a rational number and A is non-zero, then what I can do is I could define U to be 1 over A, and this is also a rational number. And moreover, I have that A times U, so that's A times 1 over A. This is 1, and U times A. This is 1 over A times A, which is equal to 1. Right? So I see that all non-zero rationals, all non-zero elements of Q are units. So these are very different. Right? We see that all non-zero elements of Q are units, whereas if I restrict myself to the integers, I only get 2 units. Okay, so the notion of unit is going to be very specific to the ring that we're working with. Okay, so finally the last kind of ring we're going to study is what's called a field. So I'll assume that F is a commutative ring with identity, and I'll assume that this multiplicative identity is not the same as the additive identity. So we're going to call F a field if every non-zero element of F is a unit. So if every non-zero element of F is a unit. So what are some examples? Examples of fields include the rationals, right? We just showed that every non-zero element of Q was a unit. The reals, similar proof to what we did for the rationals. The complex numbers, right? So these are numbers of the form A plus BI, where A and B are in R. This is an example of a field. And we've shown that Z mod P is a field when P is prime, right? So one of our theorems when we talked about the structure of Z mod N was to show that P is prime implies that every element is a unit. That's how we can reformulate that property now. One thing you might ask is, well, if I take the inverse of a complex number, how can I write it in the form A plus BI? So one thing I'll note here is that if I were to write 1 over A plus BI, I can write this as 1 over A plus BI and multiply the top and bottom by A minus BI. So I can multiply by 1. So I could take this number and multiply. And what would I be left with? I'd be left with A minus BI over, the denominator is going to become A squared plus B squared. So this is going to be A over A squared plus B squared minus B over A squared plus B squared times I. All right, so this is a number of the form a plus bi, and if we want to be really strict about it, we could write it this way. Okay, so this is how you would take the inverse of a non-zero number in the complex numbers. Okay. What about other examples? What about the integers? So z is not a field. Why is it not a field? Well, 2 has no multiplicative inverse. I can't multiply 2 by another integer and produce 1. So 2 has no multiplicative inverse, or in other words, 2 is not a unit. 2 is not a unit. Okay, so this is an example of something that's not a field. We also saw earlier that z mod 6 was not a field because 2 had no multiplicative inverse in z mod 6, or 2 was not a unit in z mod 6. Okay, so we'll stop here, and in the next video we'll discuss properties that rings satisfy.